discuss field effect transistor. This is also transistor. BZT is also transistor, but BZT is bipolar junction transistor. That is, the current conduction in BZT takes place because of two types of charge carriers, or you can say holes and electrons both take part in conduction of the current, but in FET it is only due to one type of charge carriers. That's why this FET is called unipolar transistor, where you are controlling the current through the device by controlling or varying the voltage at the gate. That is FET. Another way of defining the same FET looks like this. FET is a semiconductor device which depends for its operation on the control of current by an electric field. That's why it is called field effect transistor, because operation depends on the electric field that is due to the gate voltage. So if you are varying the gate voltage, the current conduction through the device varies. So you have control at the gate, right? So this device FET has several advantages over BJT. In terms of current conduction, if you take current flow is due to only majority carriers in FET, whereas BZT, as I said, it is due to recombination of holes and electrons. Its FET is immune to radiation, and it has got very high input impedance or resistance, you can say, less noisy than BZT. Definitely, this device is immune to noise or less noisy compared to BZT. That's why this has become popular. It is less noisy and immune to radiation, and since it is a scalable device, this finds application in most of the integrated circuits that we are using in most of the applications, right? So no offset voltages at zero drain current, and this FET has got very high thermal stability. So to represent symbolically, this is how FET looks like. This is the N channel FET and the P channel FET. Difference is here gate, the terminal gate is shown with the arrow inward, and here gate arrow is shown outward. Only that is the difference between N channel and P channel symbolically. Here between the source, you have terminal source and drain and gate actually. When you see the construction, you will find one more terminal, that is body, that we don't show in symbolic representation, and that is not required also for external connectivity, because that is a body on which this structure is developed actually. So for external connectivity, circuit connectivity and all, these three terminals are required actually. So whereas BZT, you see, just try to compare FET with BZT. Again, BZT is also three terminal device, where you have emitter from where the charge carriers are emitted, and there is a base region which is lightly doped through which current conduction takes place, and then collector you have where the charge carriers are collected. So you can compare this FET terminals with BZT terminals. It is something like this. Source is the source of charge carriers, and emitter in BZT, it is like source of charge carriers, or you can say electrons emit, or charge carriers emit from emitter, and through base they flow, and collector, at the collector they are collected. Similarly, from the source, charge carriers enter into the channel and they reach the drain. and controlling is happening through the gate. So drain you can compare with the collector, base of BZT you can compare with gate of FET, emitter of BZT can be compared with source of FET. So that is just symbolic representation, and the meaning you can compare for further analysis. So I'm sorry. Classification of FET. Field effect transistor can be classified into junction field effect transistor and metal oxide semiconductor field effect transistor. So JFET again can be classified or divided into N channel JFET and P channel JFET. So in MOSFET, again you can divide into depletion type MOSFET and enhancement type MOSFET. Again, depletion you can further classify into P channel depletion type MOSFET and N channel depletion type MOSFET. Enhancement also you can classify into P channel enhancement mode MOSFET and N channel MOSFET. So this is a basic classification how we go on studying one by one. So to begin with, just to have constructional details, let me say this is construction of N-channel FET. This is how it looks when you take the when you see the diagrams, construction diagram. You have a source sitting at one side and drain another. The charge carriers have to start flowing from this end, and they have to reach collector. And this is a path for the current flow through which charge carriers flow. And sitting at the gate, you are controlling the flow of charge carriers. So this is just an idea to give. But the circuit wise, how it looks is this is a symbolic representation, but cross-sectional view of this MOSFET, FET, if you see, it looks like this. So what it is, again, source and drain, two terminals you have, and the third terminal is a gate sitting here. So there is a channel or there is a path. We call it as a N channel because the path is created for the current flow from source to drain with this negatively charged carriers, electrons. That's why it has N channel FET we call. And you have P-type region, which are heavily doped regions, and they are connected with metal contact and given and shorted. Both the terminals, P-type materials are shorted here and connected to the gate. So any voltage you apply at the gate, you are controlling the flow of current through this channel by wearing the junction barriers. Because if you see the structure, you will find two PN junctions, PN and PN. So two PNs, they act as diode. So when you apply the negative voltage at the gate, definitely the P region, PN, this will be reverse bias because of the negative terminal of the gate voltage. That time the barrier potential will be more, and there is more opposition for the flow of current. Similarly, this side also, when you say negative here connected to P, definitely this PN junction is also reverse bias. So more barrier, more resistance and less current. So small region you will find for the flow of current, or small path for the current flow. That is how we can draw some concept from this, looking at the circuit, looking at the cross-sectional view of this FET. Symbolic representation is this, as I shown in the previous slide. A symbolic inward arrow says it is a N channel FET with the three terminals: source, drain, and gate. So next, constructional details. We have seen Next, working of N channel FET with VGS is equal to 0. Same structure FET, N channel FET I have taken, and just I have connected the batteries. Two batteries, one between drain and source, another between gate and source. Source is a common. With respect to source, I am applying the voltage at the input and at the output. So I'll keep some voltage between the drain and source, and I'll in the beginning VGS I will keep 0. With 0 volts at the VGS or at the gate, what will happen? The barrier, you can see barrier. This is the extended part. This barrier is extended, right? So there is a very less path for the current flow. If I increase negative voltage, further the barrier will increase. If I increase the positive voltage, barrier will reduce. Means this extra extended region will reduce and more path for the current flow from source to drain. That is how we can vary with this conduction path can be increased and more current you can observe, provided you apply more positive voltage here. So with the VGS is equal to 0, this is one state of the device, conduction state of the device we have shown. There is a path, but till current can flow even with VGS is equal to 0 in the device. So next you apply VGS as negative. With 0 we saw. With the negative voltage, you just see when VGS is negative till it has extended. This region, depletion region, what we call barrier is extending. So there is less, there is a path width which is reduced. Earlier it was more. The path for the current flow was more. In the sense, the width of the barrier is increased and path width is reduced. So I can say less current flows through this device from source to drain, and that is the effect you can observe. By varying the gate voltage, I can control the flow of current through the channel. So if I apply positive voltage, just reverse the battery and check. This barrier comes closer to this P region, and even this barrier or this region which is extended because of the barrier or the negative voltage, this will come closer to this, and there is a more path created for the or more region made free for the flow of charge carriers from source to drain. That is the advantage of this device. You have control over the channel or over the current conduction in the device through gate source voltage. So as an analogy, if somebody finds difficulty in understanding the concept or understanding the structure of FET, let me take some analogy. You can just compare this operation of FET to water pipe. And in the water pipe, you have a tap in your homes. So you just try to, you can control the flow of water falling into the bucket by varying the valve, right? So you can open and close the valve, right? So water flow can be controlled by controlling or turning the valves, right, that are attached to your pipe, right? So similarly, the current flow through the device can be controlled sitting at the gate. Gate is like a opening and closing of the valve when you compare with a right tap, right? Similarly, same diagram I'm putting here. Just it is an analogy to understand the concept. Just you try to link this concept to that, but technically that is what you have to follow just for understanding sake. When pipe is pressed at one end, water flow decreases. When you make it tight, less water flows into this. Similarly, you can compare the flow of current in the FET. So more the path you provide, more the water flows. How you provide that path? By controlling the gate or the valve in the what do you call, right? Tap you control on the pipe, right? Right. So now we saw this construction and just brief working of FET for negative voltage, how it behaves, positive voltage and 0 volts, how barrier varies and how current varies, we saw. Now let us discuss types of FET. We have N-channel FET and P-channel already I have told. But what exactly is N-channel and what exactly is P-channel? That is a question. Current carriers are electrons in N-channel FET. Current carriers are electrons, whereas in P-channel, current carriers are holes. Mobility of hole electrons is almost twice that of holes. It is found out that the mobility of electron is 2 times the holes, and that is meaning is electron mobility is more than the holes. So whenever you compare N-channel FET with P-channel, N-channel FETs are faster than P-channel because mobility of electron is higher than the holes. So that is why we talk more of N-channel FETs, N-channel MOSFET. Even when it comes to BZT, we talk about NPN transistor than PNP. They are also important, but as for the speed is concerned, device speed is concerned, always NPN BZT or N-channel FETs or N-channel MOSFETs are preferred. This N-channel FET has got less noise compared to P-channel, and it has got large transconductance. So transconductance is very important parameter to describe the speed or the response of this FET. Even in MOSFET, we can define this transconductance. Transconductance is nothing but ratio of change in drain current to gate source voltage. That is, it tells how fast your FET responds to change in the gate source voltage. Means it tells the response or the device speed, right? So on similar lines, we can try to plot the graphs. If you know the operation of FET, JFET, you try to observe the behavior. That is, when you vary the gate source voltage and what happens to the drain current, it varies. It increases with more positive voltage or less negative voltage. It increases. So more the negative voltage on x-axis, I have shown VGS. If VGS is more negative, current falls to 0. At VGS is equal to 0, current is maximum, right? So that is transfer characteristics. This blue line, this graph, this side is a transfer characteristics curve for FET, and this is drain characteristics of FET. Drain characteristics starts here at 0 reference, and it is varying. The current ID on y-axis is increasing as we increase the drain source voltage at VGS, 0. When VGS you have kept 0 and trying to increase VDS, your ID also increases. Meaning is, what is happening here? I have mentioned it as ohmic region, meaning is the resistance is reducing, current is increasing. The variation in the resistance, we call it is measured in ohms, so ohmic region we call. Similarly, from B point, you can see the current is constant, almost constant. So we say pinch-off region. Pinch-off region is a region where current remains constant. or pinch of voltage. You can define one more term, pinch of voltage. Pinch of voltage is a voltage above during which your current is constant. This is a pinch of point actually from which current starts. Current remains constant. But there is a limit for VDS also. Further, if you increase beyond the limit, there are chances that the junction may break down, and avalanche breakdown we call, or breakdown region, is what we have shown here. Similarly, yeah, same thing explained in detailed description. Detailed discussion is given here with the equation, ID current, how it varies, and VGS, what is the role of VGS, and VP is a pinch of voltage. So looking at this one, current equation is written, ID is equal to ID double S into bracket 1 minus VGS by VP whole square. This ID, you know, drain current that is plotted on y-axis, and IDSS is the drain current only, but at VGS is equal to 0. At VGS is equal to 0 is this point. At VGS is equal to 0, current is maximum. Drain current is maximum. That is a pinch of current, that is a drain source saturation current we call. So VGS is voltage applied, and VP is the pinch of voltage, right? So coming to next graph, again it's the same. Just every point it is discussed what is happening between B and C, C and D. Breakdown is happening. This is pinch of region. This is ohmic region. It is discussed in detail. Next, based on this analysis, final general graph, what we can plot is this transfer characteristics graph and output characteristic graph. Transfer and output characteristics or drain characteristics, you can say. So again, same thing we discussed. Left side we saw blue colored graph where I shown as negative voltage on gate increases, current falls, right? Current falls. Or you can say when you make gate source voltage less negative, current increases, and at VGS is equal to 0, at this point current is C. You get maximum current, that we call it as a drain saturation current, IDSS. That is what the current equation is shown here. Same thing what we discussed in previous slide. So meaning is what, even for negative voltage your device is conducting, but up to some point. So VGS off is voltage of gate source voltage when current is 0, right? So here output characteristics, or you can call drain characteristics. Drain source voltage you increase and note down the current, keeping VGS at some constant value. Now in the beginning, see, if I take this curve, VGS is equal to -3 volts. Next case, VGS equal to -2. Next case, it is VGS equal to -1. Meaning is less the negative voltage, more the current you can observe in the device. So VGS is equal to 0. This is a current conduction, and the magnitude has increased. Again, this is ohmic region where current is increasing. Variation you can observe. Where it is constant, it is active region or pinch off region. Again, if you exceed the limit of VDS, then junction breakdown regions are also shown. So detailed characteristics curves are given for representing the FET behavior. So this even breakdown region, it is shown beyond the VDS specified value of VDS. If you go device breakdowns, that is also shown here. And even for VGS is equal to positive voltage, negative we have seen, 0 we have seen, positive voltage, again current increases. Because in the device barrier you are reducing, minimizing to the fullest, and the current you are observing the highest, right? So based on these curves, you can define some resistance in the device. Drain saturation resistance, RDS, you can define. That is, change in the drain source voltage to, change in the drain source voltage to change in the drain source current, and that is RD. Mathematically, you can define it. This is actually change in VDS, change in ID. That is a very AC resistance. If it is fixed VDS and fixed ID ratio, if you take, that is static resistance, or you can say DC resistance, that can also be defined. So next important parameter is transconductance. I said in the beginning, transconductance decides the response of the FET, JFET. So this is a change in drain current with change in, this is not a correct one. Transconductance here, it is change in drain current with change in VGS. It should be VGS. So I'm sorry. Because input voltage sitting at the gate, you are controlling the drain current. That is transconductance, not VDS. D should be replaced by capital G, VGS. Right? Please make note of this change. Yes, next, coming to application of this FET, low noise and high input impedance amplifiers. Usually we use FETs. In RF amplifier design also, we prefer FET compared to other devices. This is a perfect current source device, as we saw in the active region, how current remains constant. Right? So FET is a perfect switch actually in most of the ICs that we develop, most of the computer application, computer chips that you develop. It is for the switching action you require, because the computer understands zeros and ones. Computer understands zeros and ones, and you have to produce 1 and 0 logics. So you need to turn on the device and turn off the device. So FET suits the best, right? So that is the reason why FET is preferred, or extended